In this video, we're going to talk about the periodic table and some of the information that it can tell us. Scientists like to organize data, and so as more and more elements were discovered, people would naturally make lists of those elements. And as the number of elements started to get filled in, scientists started to notice that certain properties would tend to repeat themselves. So they had helium, and 8 elements down the list they had neon. And 8 elements down the list they had argon, and they were all very unreactive gases. And then they had lithium, which was a very reactive metal. It would react violently when you put it in with water. And again, 8 away, you had sodium, and 8 more, you had potassium, and they all had similar properties, very reactive metals. Or we had hydrogen, and fluorine, and chlorine, all very reactive nonmetals. And so they noticed that the properties of elements tended to repeat themselves. And so the person that gets most of the credit for developing the first modern periodic table was Dmitri Mendeleev. And so he made lists of elements, but rather than just ordering them in terms of increasing atomic mass, and again, at the time they thought atomic mass was the important thing because the protons hadn't been discovered yet, he put the elements in a table such that elements with similar properties would appear in the same column. And he found when he was putting the elements into this table, sometimes elements didn't seem to fit in their particular column when he just ordered them by mass. But he noticed if he would just move them over one slot, then their properties would match up. And so he actually left spaces in his table for what he proposed were elements that hadn't been discovered yet. And so one sort of famous example of that was germanium. So at the time that Mendeleev put together his first periodic table, germanium had not been discovered yet. But when he tried to put arsenic right after gallium and below carbon and silicon in the periodic table, arsenic didn't match up well with the properties of the elements that it would have been in that column. Its properties did match up well with nitrogen and phosphorus and antimony. And so he moved arsenic over and left a space and said, there must be some element here that we hadn't discovered yet. Now, another interesting thing about the periodic table that Mendeleev noticed when he started organizing the elements this way is when he did this, not only did elements that he would put in the same column have similar properties, but those properties would change systematically as you moved down the list or you moved down a particular column. And so the really amazing thing that Mendeleev did is he said, not only am I telling you that there is an element that he called exosilicon, because it was going to be below silicon in the periodic table, not only does this element exist, and we just haven't discovered it yet, I'm actually going to predict what the properties are. And so he predicted the atomic mass. He said what color it would be. He predicted its density. He said how it would react with acids and bases. He even said what the formula would be when it formed compounds with oxygen. And so Mendeleev made these predictions in 1871. Germanium was actually discovered in 1886, and so this was a big moment of truth, right? Did the properties of what came to be called germanium match Mendeleev's predictions? Right, and so the incredible thing, and the reason Mendeleev gets, in part, so much credit for his development of the periodic table is when you compare his predictions to the measured values, he was basically spot on. He got the atomic mass, right? He predicted what it would look like. This is one that blows my mind, right? He was able to predict the density almost exactly, and his other predictions were correct. And so this gave Mendeleev a whole lot of credit in the chemistry community, and these predictions, or his matched predictions between germanium and exosilicon, were really astounding and really show us the power of the periodic table and how much information is actually stored in the periodic table. We're just going to start scratching the surface of that in this video, and throughout your study of chemistry, I think what you'll find is you'll learn more and more about the information that's actually hidden in the periodic table. All right, so first some terminology. We have names for the rows and the columns in the periodic table. We call the rows periods, And then the columns, because these are elements with similar properties, we call those groups, or sometimes you'll hear those called families. And as we mentioned, the reason we organize the periodic table the way we do is in part because the elements in the same columns or in the same groups have similar properties. Another really important thing about the periodic table is it allows us to determine, based on where they're placed in the periodic table, where are the metals, the nonmetals, and the metalloids. And so the elements in the upper right-hand corner are our nonmetals. Most of the elements in the periodic table, the ones to the left of this dividing line, are the metals. They're colored in the beige color. And then this dividing line between the metals and nonmetals, you can always make it by starting on the corner at boron and going down in a stair step. The nonmetals appear to the right, the metals appear to the left. Those elements that touch one of the faces, with the exception of aluminum and polonium, are our metalloids. And so, as we're going to see, they have properties of both metals and nonmetals. And so metals and nonmetals behave very differently in chemical reactions, and so we'll talk about what some of their properties are. I guess one important thing to notice, right, if you start the dividing line here, right, hydrogen is a nonmetal. So that's an easy mistake to make. You want to be sure to remember the nonmetals are in the upper right-hand corner, and then we also have hydrogen is a nonmetal. Shit. All right, so some of the properties of metals. I'm not going to ask you to, regurgitate these, but it's good to talk about them. They're almost all solids. The only exception is mercury, which is famously a liquid at room temperature. They tend to have shiny, reflective surfaces. What's really important for us as chemists is that metals tend to be very good conductors of heat and electricity. They're malleable, which means we can pound them into shapes. They're ductile, which means we can pull them into wires. So this is why wiring in our houses tend to be copper, a metal, and it's a good conductor. Maybe most importantly for chemistry is that we talked in previous videos about how when atoms gain or lose electrons, they form ions. Well, metals tend to like to lose electrons, and therefore they form positive cations very frequently in chemical reactions. We can sort of think about metals and nonmetals as being opposites of one another. So if metals have one particular property, the nonmetals are probably going to be opposite. So they are not malleable and ductile. Instead, we would say they're brittle. When we pound them with a hammer, they tend to smash into pieces. We can't pound them into shapes. Right? Probably most importantly, from a chemistry perspective, is while metals are good conductors of heat and electricity, nonmetals are poor conductors of heat and electricity. And while metals tend to lose electrons in chemical reactions, nonmetals tend to gain electrons, and therefore they become negative anions. Metalloids' properties are sort of somewhere in the middle, and one of the cool things about metalloids is we can actually tune their properties. At low temperatures, they're not good conductors of heat and electricity, but at higher temperatures, they are. So metalloids are also sometimes called semiconductors, and they're used very often in the computer industry because we can turn their conductivity on and off. If you think about computing, we think about bits, right, which is either 0 or 1, on or off. And so with metalloids, we can turn their conductivity on and off, so we can turn those bits on and off. So this is in part why metalloids are so prevalent and so important in the computing industry. And then this is just a reminder, I showed it before, but again, the dividing line between metals and nonmetals starts at boron. We move a stair step down, nonmetals in the upper right, metals on the left, and the metalloids are the ones that fall on the line, with the exception of aluminum and polonium, which are strictly metals. Now, some of the families in the periodic table, some of the groups appear so often that they have names, and it's important to know those names because we'll often use these names to refer to these groups. And so the ones that I want you to know are the first column are the alkali metals. The second column, except for hydrogen because it's not a metal, the second column is the alkaline earth metals. We have, as far as the nonmetals that have names that we need to know, we have the noble gases, and then we have the halogens. The oxygen family are the chalcogens, although I'm not going to ask you to know those. The ones I want you to know are the noble gases, the halogens, alkali metals, alkaline earth metals. And then while they're not strictly families, I think it is important to know that I sort of think about the periodic table as being a distorted Batman, right? You've got Batman's head, and then here are his ears, right? Batman's head, where the ears aren't, those are our transition metals. And then the two rows, or the two periods, that sort of come out of the periodic table and are written below, they have names. They're the lanthanides and the actinides. All right, so one of the most important things that the periodic table can tell a chemist is it allows us to predict the charge of many elements based on their position in the periodic table. And so for metals, we know that they tend to lose electrons and form positive ions, and nonmetals tend to gain electrons and form negative ions. And then metalloids can be both, and so pretty much all nonmetals, we know what charges they're most likely to have based on their position in the periodic table, and for a lot of metals we can predict. And so let's look at a periodic table and see which elements we know what their charges are going to be when they have charges. So first, let me say, atoms aren't always ions. As we'll see, sodium, when it's an ion, likes to be +1, but sodium isn't always +1. We can certainly have neutral sodium atoms. All right, but how do we predict what the charges are going to be? Well, as we're going to learn towards the end of the semester, the noble gases are incredibly stable based on their number of electrons. The number of electrons that they have gives a particularly stable arrangement. And so in chemical reactions, atoms tend to like to form or obtain the same number of electrons as noble gases. The nonmetals tend to do that by gaining electrons, and the metals tend to do that by losing electrons. And so for fluorine, if it wants to have the same number of electrons as its closest noble gas, that's neon, it needs to gain 1 electron. Chlorine can do the same thing. If it gains 1 electron, it'll have the same number of electrons as argon. Bromine can gain 1 electron and look like krypton. So the halogens tend to like to form ions with -1 charges. Right? And if we think about oxygen, right, it's 2 away from neon. So if it adds 2 electrons, it can go from 8 electrons to 10 electrons. And so oxygen and its column, like to form -2 charges. Nitrogen, -3. I think it's important to remember the dividing line between metals and nonmetals. Right, so arsenic is a metalloid, so it can do a lot of different things, but nitrogen and phosphorus, they like to be -3. Oxygen, sulfur, selenium like to be -2, and our halogens like to be -1. So the nonmetals and carbon, I think we see less often as a -4, but we certainly see it. All of the nonmetals, we are able to predict what their charges are going to be when they form ions. We know a lot of the metals, but not all of them. So lithium, if we think about it wanting to have the same number of electrons as a noble gas, if it's going to lose electrons, right, it's going to go from 3 to 2 to look like helium, and so it needs to lose 1. Sodium has 11. If it could get 10, it would look like neon, so it needs to lose 1. Same thing with potassium. So if the alkali metals lose 1 electron, they'll have the same number of electrons as the noble gases, and so they tend to form +1 ions. And it might make sense, beryllium and the alkaline earth metals like to form +2 ions. Now those are most of the metals that we know. It turns out most of the other metals can form multiple charges, or as we'll see later in the semester, we also sometimes call charges oxidation states, depending on the compound that they're in. So other than the alkaline earth metals and alkaline earth metals, if you just gave me manganese, for example, I couldn't tell you what the charge of the ion that's going to form, because it has multiple possible ions that it can form. But there are 3 others that tend to only form 1 ion that we will encounter enough that I ask you to know. So, and they are aluminum, which like to form +3 ions. And that should make sense, because aluminum has 13 electrons. If it wants to look like a noble gas by losing electrons, its closest noble gas is neon. So if it loses 1, 2, 3, it would have 10 electrons like neon. So aluminum really only forms +3 ions. And then the other two that are predictable that I want you to know are zinc at +2 and silver at +1. And the way I remember these guys is they sort of go in a stair step down, right? They're sort of going diagonal here, and we go 3, +3, +2, +1. So the nonmetals, when they form ions, we are always able to predict what their charges are. The halogens, -1, the chalcogens or oxygens family, -2, nitrogens family, -3, carbon, -4. When the alkali metals and alkaline earth metals form ions, we always know what their charges are going to be. The alkali metals will always be +1. The alkaline earth metals will always be +2. And then we also know that when aluminum forms ions, it will be +3. Zinc ions are always +2, and silver ions are always +1. Any of the other metals, all of the other transition metals, the other main group metals down here, like lead and tin, and the lanthanides and actinides, we cannot predict their charges just based on telling you what the element is.